here, we're looking at a function that has both, again, it's in factored form, and it's really similar to the one we just did. If you look at it, it's x minus 1 squared this time, x minus 3 squared, that was still the same as in the first one, and then x minus 5 was still the same. So we just kind of have an extra squared here in the front one. So if we go to our degree, it's basically 2 potential x-intercepts from this first one, 2 potential from the second, and 1 here in the back, so a total of 5. The number of turning points is always going to be 1 less than that, so 4. We're going to have 4 curves on this graph eventually. Our x-intercepts, we find that when we set y equal to 0, which in this case is f of x, so x minus 1 squared times x minus 3 times x minus 5, and that x minus 3 was squared. Setting each of these equal to 0, I'm just going to do the ones that repeat. I'll just list them once since we kind of have a general idea of what we're going here with this. So I have an x-intercept at 1, again at 3, and again at 5. So really what we're going to be doing is seeing how much does this graph actually change by just squaring that x minus 1. How much is this changing? Well, you can tell already by the degree, but we'll keep going from here. The y-intercept, we're going to go 0 in for our x values, 0 minus 3 squared, and 0 minus 5. So y is equal to negative 1 squared times negative 3 squared times negative 5. So y is equal to 1 times 9 times negative 5, which in this case now is going to be a negative 45. Okay, sign chart. So let's draw. Here we're going to put our x, always our x intercepts are the only thing that's going to go on this sign chart. So 1, 3, and 5. And we're going to pick numbers to the left and in between and to the right of all of these x-intercepts. So the number to the left of 1, great one would be 0 because we kind of already found that one for us. 2, 4, and let's say 6 again. Okay. So 0, when I plugged that in, it gave us a negative 45, so we're down here at negative. I'm going to kind of clean up our function here just for a second so we can test it a little bit better. Alright, so when we go into test like x equals 2, let's go back to really analyze. You see how this front parentheses says it's squared? So no matter what I plug in for x and I subtract 1, I've got to eventually square it, and whenever you square anything, it always comes out positive. So I really don't even have to worry about that part. I can kind of knock it off because it's always going to be positive. Same thing here, it's always going to be positive. So we can kind of cheat and just say, hey, when I test, let's just plug in this back part. 0 minus 5 was negative 2, so 2 minus 5 is negative, 4 minus 5 is negative, and 6 minus 5 is positive. We can't always do that every single time, but it was a kind of really cool thing, mainly because they were being squared. So, alright, so we are above the x-axis only from 5 to infinity, and that's it. We're going to be below the x-axis. I want to make sure I do these all in their intervals. So starting at negative infinity up to 1, between 1 and 3, and then between 3 and 5. The last thing we have to find is the end behavior. So the end behavior, the degree itself is odd. So that tells me with an odd degree that my ends are going to be split. It's not like both up and both down or something. It's one's going to be down on the left or up on the right or vice versa. And the way to determine which one's which is to go to our leading coefficient. Well, there really wasn't a negative out front of all of this, so our leading coefficient's positive, which tells me that I will eventually be down on the left and up on the right. Or in that fancy notation, that my y values should be decreasing as I go left on that graph, and my y values should be increasing as we go right on that graph. Okay, so coming back in here, we're going to draw our graph. We have an x-intercept at 1, 3, and 5. We now have a y-intercept way down here at negative 45. Our graph tells us that we should, as we leave that right side of the graph, our end behavior tells us we should be up, and as we leave this left side we should be down, which is good because we have to be crossing through that. It's not a perfect line, but we should be crossing down through that y-intercept way down there. Okay, so at our x-intercept of 1, it's telling me I'm coming from below, and after I hit it, I should still be below. So that tells me I'm coming up, touching it, and coming right back down. So I cannot go above. There's no plus signs up here. Same thing here at 3. I'm going from below. Once I go past it, I'm still below. So I'm going to be curving somewhere, coming up and touching it, and going right back down. Finally, at 5, I go from below to above. So that's right there is telling me when I have a true cross through my x-axis. So here, right here is a good estimate, again, of the function. We might not know, again, how low these dips go, but this is a really good estimate of it. All right, let's go to example C. In example C, you'll notice that we finally have a function that's not already in factored form, so we kind of need to start with that first. But first things first, they want to go and we want to get the degree, and the degree is always your highest powered exponent. So in this case, it's 3. The number of turning points is 1 less than that, so there's only going to be 2 turning points on this graph. Our x-intercepts, when we find that, we just plug 0 in for f of x or 0 in for y. And here, because it wasn't done for us already, we're going to have to do the factoring first. So let's pull out what's common, which is an x. And if I look to this, not quite done, because 9 minus x squared is actually a difference of cubes. 3 minus x and 3 plus x. So let's set x equals 0, 3 minus x equals 0, and 3 plus x equals 0. So we get an x-intercepts of 0, x equals, move that x over, so 3, and then x equals negative 3. So we have 3 x-intercepts. There was 3 for a degree, so that's a good sign. Our y-intercept, we get that when we plug 0 in for x. So 9 times 0 minus 0 cubed, pretty simple. It's 0. All right. After that, we want to figure out when we're going to be above and below. So let's put our x-intercepts on here. Negative 3, 0, and 3. And let's test. Anything to the left of negative 3, I'll keep it small. I'm going to go negative 4. Anything between negative 3 and 0, let's say negative 1. 0 and 3, we'll go positive 1. And anything to the right of 3, maybe we'll go 4. And now from here, I could choose. These numbers I want to test, I can either put them in the original function, or I could put it in the factored form. I'm actually going to try it right here in this factored form because sometimes it comes out a little easier. Because look at this. If I plug negative 4 in, this first part, obviously it's negative. 3 minus negative 4, that's a positive number. So we have a negative times a positive, which is negative. And 3 plus a negative 4 is negative. So a negative, positive, negative is going to be a negative. Okay, so a negative 4, a 7 right there, which is positive, and another negative right there, a negative, positive, negative is actually going to be positive. If we try negative 1, a negative right there, a positive right there, and a positive right there. So a negative, positive, positive will come out negative. If we try x equals 1, a positive, and a positive. So it looks like 3 positives, going to make a positive. And last but not least, 4 will be positive in the front, negative in the middle, positive in the back. So positive, positive, negative will come out negative. So we are above the x-axis, starting at everywhere left, so negative infinity up to that first x-intercept at negative 3, and then everything between 0 and 3. We are below the x-axis from negative 3 to 0, and then from 3 to forever on the right, so it looks like to positive infinity. Our end behavior. Our degree looks like it is odd, so that tells me my ends are going to be split. So the degree is 3, and then the leading coefficient, if we go up there, that x cubed, it's actually negative. So when the degree being odd tells me I'm split, with the leading coefficient negative, it tells me that I should be up eventually on the right and down on the left. I'm sorry, up on the left and down on the right. I drew it correct, but I kind of said it wrong. Alright, so my function basically says that my y value should be going up as I go left on that graph, and my y value should be going down as I go to the right on the graph. Alright, so let's put all this information together and let's see what we can do as far as drawing a graph. So it tells me I have my x-intercepts at negative 3, at 0, and at positive 3. I've got a y-intercept, at least is a little nicer this time, but it is only at 0, so I'm going to keep it there. The end behavior tells me that after I leave on that far left, my last x-intercept, I should be up, and after I pass through or touch that last y-intercept or x-intercept on the right, I should be all the way down. Okay, and then let's go to our sign chart to tell us in between stuff. So everything to the left of -3, I should be above, which is good. All that right there, we're above. Now after I pass -3, I should be below, so that's telling me I'm going to cross through. At 0, I'm going to go from below on the left to above on the right, so I know I'm crossing through. And then at 3, I'm from above on the left to below on the right, so I'm crossing through. All we've got to do is just kind of get a general idea of what's happening in between, however high I feel like drawing those humps, and then we can call it done. So here is a great idea of what the graph for this last function is going to look like. So moving on, here's example D. And what I really want to do with this one is give you guys a chance to look at this. Let's pause it. Why don't y'all try it yourselves, and let's come back and compare some information.